Well, hi there, Nick here, M0NTV, and welcome back to my shack and to another video. And this one is by popular demand. A number of people have contacted me and asked me about the digital oscillators that I use in my radios, and you can see this multicoloured one here just behind me, which is identical internally to this one here, and this is the one we're going to have a little look at. Now, of course, you wouldn't have to necessarily build the whole thing in a tin. It's just it's useful for me because I do a lot of prototyping to have one of these. You can just pull off the shelf and it's all there. You know, you just plug it in and hook up a couple of bits of coax and throw together a superhet in a few minutes. So it's yeah, a useful thing. Now, the guts of this is this amazing little thing, which matches my my shirt. This is an SI5351 breakout board. The actual SI5351 chip is tiny. I'll show you in zoomed in a moment. And this little thing, which costs just a few pounds, UK pounds, has been an absolute game changer for ham radio homebrew, because it will provide three independent RF signals from 8 kilohertz to 160 megahertz, it says. Amazing. But to leverage the power of this in your radio, you need three other things. You need a microcontroller to control it. You need a rotary encoder to adjust the frequencies that you're producing with a switch so you can change the increments of your tuning, and you need some kind of visible feedback of what you're actually doing, so an LCD screen. So that's what this is, all in one. That's what we're going to be looking at today. I'm going to show you what I built, how I do it, how I calibrate it, and as always, hope you enjoy.
And so here we have the SI5351 breakout board zoomed in a bit, and you can see the actual SI5351 chip itself just under the clock 1 letters in the middle there, and the 25 megahertz crystal just underneath it. So what is it? Well, it's a phase locked loop signal generator board, essentially. It comes usually with a strip of header pins there, top left, which you solder in. And then you usually get 3 SMA connectors as well, which go on those 3 strips at the top. Some people don't bother fitting them, they just hardwire the coax in. You can do that if you wish. I tend to solder them on. You don't necessarily need to solder them all on. Usually in a conventional superhet, your single conversion superhet, you'll only need 2 frequencies. So generally we use clock 0 and clock 2. Clock 0 we generally use for the VFO, for the variable frequency, so that's what you'll use to tune. Clock 2 will be for the BFO, the beat frequency oscillator, or the carrier insertion oscillator, so that will usually be a fixed frequency, which will be at your IF frequency. Yeah, now the reason we generally use clock 0 and clock 2 is just to provide a bit of physical space between those 2 RF ports, and so we kind of leave clock 1 blank. Now actually in the tin that I did, I put them all on, but I only actually use 0 and 2. Now the header pins, some of those are breakouts as well for those clocks. I generally solder them all on, but you don't need them all. In fact, you only need 4 pins, because it works on the I2C bus, which means you'll have a V in. It will take 3.3 to 5 volts. There is a regulator on it, but generally I will run it at 3.3 volts from the microcontroller, a ground, and then an SDA, the data, and an SCL, the clock. and they will connect to your I2C ports on the microcontroller. So that's it. What we'll do now is have a look at how this all fits in together with the other peripherals as well.
Now you will see that the microcontroller that I'm using is an Arduino Uno. You could of course use an Arduino Nano, which is electrically the same, it's just a smaller form factor. I happen to have a few of these, so that's what I used. You could use something that was much more powerful if you were going to do something more elaborate like a Teensy, or maybe something like an ESP32. You know, I mean, there's a lot of choice around. But what I'm trying to do here is to keep this as simple as possible. So I have built a dedicated software-defined radios which used a Teensy and did a lot of software functionality. Here, not so much. And the last few radios that I've built I've used this basic setup, and it is very basic. So there's no flash TFT screens or anything like that. It's just a simple 16:2 LCD display, and it has the connector on the back. So again, you've just got 4 different connections: the 5 volts, the ground, and then the data and the clock. So you'll see how all these things fit in together. So it's not that bad really. The SI5351 we've already mentioned. You've got the clock and data there. Now on your Uno, if you're going to use an Uno, you may well have dedicated data and clock I2C headers that you can plug straight into. On the one I have, I think I'd got some, but you can also use analog pins 4 and 5. So analog pin 4 is the data and analog pin 5 is the clock. So I'm using both here. So the SI5351, it's getting 3.3 volts from the Uno, and it's connecting into pins 4 and 5. The LCD needs 5 volts, and that's going straight into the dedicated SDA and SCL ports. And then the rotary encoder needs 5 volts, and that is going into digital ports 2 and 3. And then the switch, which controls the increments of the tuning, that's going into analog 3. And that's it, really. I do most of my switch debouncing within software, so which is why you don't see any resistors. Your mileage may vary, and you know, people construct 10k resistors off the switch ports and things like that. So you'll have to kind of make your own mind up about that. But I've found using the sketch that I'm going to show you in a moment, it does seem to work pretty well, and is pretty well behaved with the software debouncing. Now, if you've never done anything with a microcontroller before, if you've never played with an Arduino Uno before, then what you probably need to do is just press pause on this radio project at the moment, and just put it to one side and just get familiar with using this stuff. Because I remember when I came to the Arduino, it was because I wanted to do exactly this, and I couldn't do it because I just didn't know enough stuff. I just wasn't familiar enough with how you connect all these things together, and I just, you know, so I had to just deliberately put it aside and just go back to basics and do some tutorials and just learn how to use the thing. And there's some excellent material on the internet for basic tutorials and using the Arduino Uno. And do those things. So start with a blinking LED and then work your way up and just get familiar. So learn how to connect the LCD screen to your Arduino Uno and just get used to what that looks like and what you can do in the code. Learn how to connect the rotary encoder in, and there are sketches that enable you to just increment and decrement a value. And so just get familiar with it, and then learn how to connect the SI5351 in, and then once you're happy that you know what you're doing with it, then by all means have a stab at this. But if you're just kind of following along and you've never done any of this stuff before, if it doesn't work, you're going to have a heck of a job trying to find out why it doesn't work. Whereas if you're a bit more familiar with it, you'll know some of the things that can go wrong, and some of the mistakes that can be made, and how to fix them. That would be time very well spent, I would counsel.
So here is my little oscillator. So 16 by 2 LCD display. I managed to get some little plastic bezels from a guy on the internet, which is very good. Unfortunately, he only seems to do them for this. It'd be good if you could get these for other, larger TFT screens, and so I suppose you could 3D print your own, whatever, if you've got the capability to do that. Anyway, so yeah, that's that. Rotary encoder, of course, over here. Breakouts here for the RF connections, and then on the side, just roughly, really, the power, and then the USB-A port, a little bit oversized, that hole, never mind, so you can program it. Right, well, let's take the lid off, and I'll show you what it looks like inside. So here is the same tin with the lid taken off, so you can see the Arduino here, the various connections, and here's the SI5351 down here, and then on the actual lid, this is the LCD display with the I2C little board that rides on the back of it to save you from having to make loads and loads of connections, and the rotary encoder. So it all fits in there quite easily, and yeah, it seems to work pretty well.
Right, well, once you've got it all put together and wired up, you're going to need some software, right? So what are you going to need? Well, my sketch requires, I think, 4 libraries. One of them is Wire. Well, that's a standard Arduino library. The other 3 are the LCD library. There's one for the rotary encoder, and the third one is Jason Mildren's EtherKit SI5351 library. And actually, those 3 libraries that are not part of the standard Arduino installation, I have put in a folder on my Google Drive, and I've shared the link below. Also, there is my code for the digital oscillator. I say mine, I've just borrowed other people's work and adapted it, so I take no credit for that at all. But people were kind enough to share it with me, so I'm paying it forward and passing it on to you guys as well. I've tried to comment it as much as possible. We will have a look at the code in a moment. And also the wiring diagram is there as well. So the link is in the description, and so I hope that's of some help. What you need to do first, once you've got all that, and again, if this is unfamiliar with you, park all this right for a minute and just get familiar with the basics of using an Arduino. You don't have to be a coding ninja, but you do have to know about installing libraries and the rest of it. Otherwise, it'll do your head in. So make sure you can you know your way around that. The first thing you will need to do before we get into my code, we'll look at my code in a minute, is to calibrate your SI5351. Very important. And the next bit, I'm going to do a demo of just that. Now, when it comes to calibrating, there's one way of doing it, but there's many ways of measuring it, if you like, because it involves sending a signal out from the SI5351 and measuring it. Now, as you'll see in a moment, I am now the proud owner, finally, of a Spectrum analyzer, a Siglent, which is wonderful, but it's taken me years, to be honest, of building radios before I ever even considered that it was worth the financial outlay, because they are expensive, right? And I don't want to give the impression that to do this you've got to have megabucks and because you don't have. And I've built many radios before I had a spectrum analyzer, right? So yeah, it makes life easy, but you don't need that. What we're actually going to use is one of these, a little San Jian Frequency Counter. Brilliant little things, and essentially, you know, two wires there, so you plug it in. You can fit it 9 volts, 12 volts, and I put a little BNC connector on there for the signal coming in, and it works really well. And it's about £15 UK money, you know, so not very much really. Certainly not when compared to a spectrum analyzer. And it works really great. So this is what we're going to be using to calibrate our SI5351. So here is how to calibrate your SI5351. So what I've done is I've opened up the calibration sketch in Jason Mildren's EtherKit library. And so compiled that and uploaded that to the Arduino. And then I've just opened up the serial monitor. Make sure that you've got the right baud rate. It's at 57600, otherwise you won't see anything very meaningful. And the instructions come up here. Now what's happening, what the sketch is doing, it's getting the Arduino to get the SI5351 to output a signal at 10 megahertz on port 0. What it thinks is 10 megahertz. And then what we are doing, and you'll see there in the little cutaway, I've got the Arduino and the SI5351, it's all in the little case, of course, connected to the San Jian Frequency Counter, and I'm going to switch it on. Right, so, and you will see that we're reading, well, about 300 hertz too high. That's okay, because that's what this calibration sketch is designed to correct. So really, we want to try and get it as close to 10 megahertz as possible. And the way you do this, if you look at the screen, you can change in software the frequency by different kind of incremental values, ranging from a tenth of a hertz here to 10 kilohertz here. So now, if we're reading 300 hertz too high, we obviously want to go down. So if you look at the down, so if I input a K, that will reduce should reduce the frequency by 100 hertz. So we do. So you keep an eye on the frequency counter. I'm going to input a K, and when I press send, there we go. So it's 100 hertz. So I need to basically do that again twice here. So we'll send another K. Yeah, takes it down to 96. And you'll notice the current difference is being logged down here. We'll get to that in a moment. And we'll send another K. And so that takes us down now to, just under. Now, what we could do is bring that up. So we could bring that up now by 4 or 5 hertz, which would mean using the Y. Okay, so let's do that. There we go. I'm just sending these 1 hertz things, and we're about there, aren't we? So that would give us, you see here, a current difference of 29,600, and that is your calibration factor that you will need to remember. Write it down. What I do is I write it on a tiny little sticker and put it actually on the board on that SI5351
On this particular oscillator, it's on a sticker on the back of the tin, so I know what it is. And that is the value you'll be using in your code, in the actual sketch for the digital oscillator, and that will make sure that when you are producing frequencies, they're as accurate as you can get them to be. Now, if you're wondering about how accurate this little San Jian frequency counter is, surprisingly so, because I actually used the 10 megahertz test signal, the external reference signal from the back of the Siglent spectrum analyzer as a reference, and it proved to be, well, somewhere between 4 and 5 hertz too high. It was reading, so between 4 and 5 hertz too high. So in actual fact, what that means is that I'm quite happy for it to sit at about 4 or 5 hertz under 10 megahertz, because I know that is actually more accurate. So for myself, I would actually go for the 30,000 mark here, because I know that frequency counter is a little bit off. But even if I didn't, at the end of the day, you know, the person that comes back to you on the air and tells you that you're 4.5 hertz too high has either got far too much money to spend on an expensive spectrum display, or far too much time on his hands. Is all I can say. So I wouldn't worry too much about that. So this little counter is absolutely brilliant, and you'll have seen me use it before in collaboration with the little test jig for measuring the frequency of crystals, for matching crystals for your crystal ladder filter. So yeah, really brilliant. It cost about £15 or something, I think. But yeah, really good. So so that's how you calibrate your SI5351.
And finally, let's have a look at my code for the oscillator itself. I've credited the people who have done all the heavy lifting in this, and as I said, really all I've done is tweaked it and added a few little bits and pieces. So essentially, I mean, you'll be able to have a look at this yourself. This is very basic. There's not loads of bells and whistles in this at all. The first thing to note is what you do. You've got 4 choices with what you do. You can run this with a direct conversion receiver. You know, what you see is what you get, basically. So you'd need to uncomment that. I've got this uncommented at the minute on the IF offset. So this, if you're doing a super het, this will enable you to do that. Now, there's some things you need to fill in. I've tried to explain here, setting up the VFO and BFO of what you do, and this is just what I do. So, you know, whilst I'm happy to get feedback on all this stuff, I'm not the world's best coder. I've coded things on and off for years, really, but I'm certainly not an expert at this, as I am expert at any of it, really, to be honest. But please don't send me emails saying, I tried your code and it doesn't work. Because there's a million and one things that would stop that happening. Usually it's libraries. Very often it's libraries where you've got the right libraries installed properly, and these are the libraries here. As I said, this one, and this one I've actually put in the Google Drive, so I know those versions work with this version of the code. Now, essentially what you do for USB, you have an LSB and a USB figure here. What this figure is the top edge of your crystal sideband filter, and I add an optional 300 hertz offset. What that does, it attenuates the lower frequencies and allows more of the higher frequencies to get through. And on LSB, what you do is to avoid the sideband inversion. You take the figure, which is the top end of the top edge of the filter, minus the filter bandwidth minus your optional 300 hertz, and that's what that gives you. So when you do that, that's what you get here. And because this rig will be on 17 meters, I'm setting the BFO to the USB setting, so that will be there. In the VFO setting, you put the lowest frequency that you want to use to tune. So I've got 18.068 megahertz. You can change the step size that you want to start off with as well, and I've started with a 1 kilohertz at a time. I'm not going to go all through this, and you don't need to know exactly how all of this does what it does to use it. You can change the splash screen. That's easy enough to edit. If you want to put your own details there and do what you want with that, it is fine. Here, where it's the SI5351 calibration correct factor, here, this is where you put that calibration factor that you got when you used the calibration sketch. That's where you put that in, and that will make sure that that's fine. You can set the drive strength, and I've got it set, despite what I've put here in the comments, I've actually got this set different levels. It goes from 2 milliamps to 8 milliamps. Depending on what mixer you're using, if you're using an active mixer, you won't need as much drive. If you're using a passive one like I am, generally you need a bit more. But again, your mileage may vary. Really, you've just got to try it and see. It's only by experimentation you work out what the drive is and what you can do. I mean, you can always set more drive than you need, and then if you work out it's 3-4 dBs too much, then you just build a little pi attenuator and stick that in on your mixer port. So that's what I would do. I have done a little bit here, which was not in my original code, about the transmit or receive. I will do a separate video on the transmit receive switching. Generally speaking, I don't get the Arduino involved with it at all. I just have, when you press the PTT, I have that grounding a relay, and then it all just switching, either into transmit or receive, and then different modules getting power and different signals being routed in certain directions. But I did see something by another fellow homebrewer who I greatly admire, Paul Taylor, VK3HN, and some of his code ones. He used the microcontroller to control the transmit and receive switching. And the advantage is, of course, if you get the Arduino to do it, you can actually put a little bit of delay in it. And where that can be helpful means you could make sure you could kind of have it switched in 2 stages, so you could kind of make sure all your routing relays are switched first, so that the signals go in the right place, but delay perhaps switching the bias onto your PA or maybe even your driver as well, until you know that the signal switched in the right direction first. Whereas if it all goes on at the same time, you might get a bit of a spike. I've not done it before, so again, that's just something I'm playing with. But you don't necessarily need to do this thing. The other thing is it switches on an LED, just so that you know when you're transmitting, as it were. But that's just an optional extra bit, really. So that is the code that I've used, and as I've done, by all means take it, adopt it, play around with it, and do what you like. There's lots of other ways of doing it. I'm not trying to pretend it's the best way. It works for me anyway. Just to show that it does, in fact, actually work. What I did is I went through and recalibrated the SI5351 and actually settled on a slightly different calibration factor. In the end, I went for 29,700, and actually that proved to be even more close in than before. So what you're seeing here is my spectrum analyzer has a web server, so you can kind of log in on your browser and see what's on the screen of the spectrum analyzer, which is very handy for doing videos like this. So this is port 2. So this is the BFO, which you remember in the code is put down nominally at 13,327.9 kilohertz. That's the IF frequency, and you'll see there that it's 13,327.894, so 6 hertz low. So that's absolutely fine. So that is the BFO, and I will show you now the VFO, our variable frequency. So remember, that's the IF frequency, 13,327.9 kilohertz, plus the lowest frequency that we want to receive and transmit on, which is 18,068 kilohertz, which, when you add those two together, it gives us a VFO frequency of 31,395.9. And as you'll see there, what we've actually got is 31,395.885. So 15 hertz low. I mean, obviously you're coming up against the accuracy of the spectrum analyzer as well when you worry about a few hertz here and there. But I don't think anybody's going to call the frequency police because of that. So yeah, pleased with that. And if these vertical divisions are 1 kilohertz wide, so if I just lean over and tweak it up, you'll see, yeah, we're moving up by 1 kilohertz and down. So yeah, very pleased with that, and good to see that it actually works. So there you go. Sorry, it's a bit of a long one this time, but quite a lot of stuff to kind of get through. One thing I did mean to say, but I forgot, was that when you're powering your Arduino Uno, you can power it at 12 volts, but that's very much the upper level of its tolerance. So in fact, what I tend to do these days, I didn't do inside that one, I just send it 9 volts, I regulate it further down the line. But in the last one I built, I do send it 12 volts, but I have a little 9 volt regulator actually in the tin, which does that job, so I don't even have to worry about it. And that keeps it nice and happy. Anyway, thank you ever so much for watching. Hope you found that helpful. By all means, check out the downloadable resources in the link in the description below, and have fun, and I'll see you on the next video. Cheers, bye bye.